Jupiter's magnetic field is unlike anything we've seen in our solar system. The northern hemisphere's field sprouts wildly like weeds, while the southern field plunges back into the planet in a completely different pattern. This bizarre magnetic asymmetry has left scientists puzzled since Juno's 2016 discovery. Like unruly vines that reveal unexpected forces beneath the soil, these chaotic patterns suggest something extraordinary happening inside the gas giant. What mechanism allows Jupiter to maintain such a complex, lopsided magnetic configuration? The answer remains elusive, but its implications could fundamentally reshape our theories of planetary formation throughout the cosmos. This magnetic mystery may hold clues to processes we've never before considered and how worlds like ours come to be. The limitations of past Jupiter missions. For over 30 years, scientists have sent spacecraft to study Jupiter, yet these missions have only managed to document a fraction of the gas giant's complex systems. Our knowledge of Jupiter has evolved through successive missions, each revealing new aspects of this massive planet, but significant gaps in our understanding remained until recently. The Galileo mission, launched in 1989, represented our first dedicated attempt to study Jupiter extensively. After arriving at Jupiter in 1995, the spacecraft spent 8 years orbiting the planet, capturing images and collecting data that transformed our initial understanding of the Jovian system. Galileo confirmed the existence of a liquid ocean beneath the icy crust of Europa and observed the intense volcanic activity on Io. The mission also delivered an atmospheric probe that plunged into Jupiter's clouds, providing our first direct measurements of the upper atmosphere's composition. Despite these achievements, Galileo's design created substantial limitations. The spacecraft followed an equatorial orbit that kept it far from Jupiter's poles, leaving these regions completely unexplored, akin to studying Earth while never observing the Arctic or Antarctic. This orbital configuration meant scientists could only view a narrow band of the planet, missing crucial atmospheric dynamics occurring at higher latitudes. Additionally, Galileo's instruments can only capture the uppermost cloud layers, essentially seeing only the cover of Jupiter's complex atmospheric book without reading any of the pages beneath. When the mission ended in 2003, scientists had collected beautiful images of the colorful bands and the Great Red Spot, but gained little insight about the structures lying even 50 kilometers below this visible shell. Technical constraints forced Galileo to maintain a safe distance from Jupiter's intense radiation environment, which prevented precise measurements of the planet's magnetic field. During one close approach in November 2002, radiation levels overwhelmed the spacecraft's shielding, causing temporary instrument failures and corrupting nearly 75% of the data collected. This radiation hazard, the most intense in our solar system, created a frustrating paradox. The closer Galileo needed to approach for better measurements, the more likely it would suffer critical damage. The fragmented data from Galileo and earlier Voyager flybys left scientists with fundamental questions unanswered. How could Jupiter's Great Red Spot persist for centuries when similar Earth storms dissipate within weeks? Why did Jupiter's upper atmosphere measure nearly 600 degrees Celsius when theoretical models predicted temperatures below 200 degrees Celsius? The planet's water content, crucial for understanding its formation, remained unmeasured below the cloud tops where most water existed. These gaps were particularly frustrating because Jupiter's formation history holds keys to understanding our entire solar system's development. Jupiter's atmospheric patterns particularly challenged scientific models because they displayed unexpected stability. The distinct bands maintained their structure for decades, despite turbulent fluid dynamics that should disrupt them. Computer simulations consistently failed to reproduce these stable patterns without introducing special conditions that lacked observational support. With Galileo's limited view, comparable to trying to understand ocean currents by only observing surface waves, scientists couldn't determine what mechanisms maintain these enduring atmospheric structures. NASA recognized these scientific gaps and began developing a mission specifically designed to answer these open questions. The Juno mission would take a radically different approach, flying closer to Jupiter than any previous spacecraft. and following a polar orbit to observe regions Galileo never saw. The spacecraft would carry instruments capable of peering hundreds of kilometers below Jupiter's cloud tops to finally read the pages of Jupiter's atmospheric book, measuring its gravity field, magnetic field, and deep structure with unprecedented precision. Engineers designed Juno with a radiation-hardened vault to protect its sensitive electronics, a titanium box with walls over 1 centimeter thick, allowing the spacecraft to venture into regions where radiation levels would destroy conventional electronics within minutes. This innovative approach would enable Juno to make measurements from just 4,200 kilometers above Jupiter's cloud tops, compared to Galileo's closest approach of 261,000 kilometers. As NASA prepared for Juno's 2011 launch, the scientific community buzzed with anticipation. After decades of seeing only Jupiter's atmospheric facade, they would finally glimpse its inner workings. The mission promised to reveal the secrets of Jupiter's powerful magnetic field, 14 times stronger than Earth's, and mysteriously more complex than theory predicted. Scientists would finally determine whether Jupiter possessed a solid core, or if extreme pressures created exotic states of matter unlike anything we experience on Earth. The mysteries that had frustrated planetary scientists for generations were about to yield to new technology and a bold mission design. Juno would transform our understanding of gas giants from broad generalizations to detailed specifics, potentially forcing revisions to fundamental theories about planetary physics and formation. With each planned polar pass, Juno would collect data that might solve the puzzles previous missions couldn't address, revealing not just Jupiter's secrets, but perhaps also clues about our own planet's distant past and the mechanisms that shaped our entire solar system, engineering a mission to survive Jupiter. Designing a spacecraft to visit Jupiter presents a fundamental contradiction. Scientists need to get close to the planet to collect meaningful data, but proximity to Jupiter exposes the spacecraft to potentially fatal conditions. At its core, Jupiter creates one of the most hazardous environments in our solar system, particularly for electronic equipment. The planet produces radiation levels so extreme that conventional spacecraft components would fail within hours of close approach. The primary source of this danger comes from Jupiter's immense magnetic field, approximately 20,000 times stronger than Earth's. This powerful magnetic field traps high-energy particles from the solar wind, accelerating them to nearly the speed of light and creating radiation belts that encircle the planet. Any spacecraft entering these regions faces a continual bombardment by these particles, which can penetrate shielding and cause cascading failures in electronic systems. When NASA engineers began planning the Juno mission, they faced radiation exposure levels that exceeded any previous planetary mission. The radiation near Jupiter is approximately 10 times higher than the already dangerous levels around Europa, one of Jupiter's moons. This extreme environment would subject the spacecraft to the equivalent of 100 million dental X-rays over the course of its mission. Standard spacecraft electronics simply could not withstand this level of radiation exposure. The engineering team faced a particularly challenging problem because Juno's scientific objectives require getting exceptionally close to Jupiter, within just 2,200 miles of Jupiter's cloud tops. At such close range, the radiation exposure would be at its most intense, while previous missions like Galileo maintained much greater distances from Jupiter, limiting the precision of their measurements. This radiation created cascading engineering challenges throughout the spacecraft design. Solar panels are particularly vulnerable to radiation damage as high-energy particles gradually degrade solar cells. Computer systems face even greater risks as radiation can flip its memory, corrupt software, and permanently damage processors. Sensors and scientific instruments can produce false readings or fail entirely when exposed to intense radiation. Engineers needed to balance protection against practicality, finding the minimum shielding necessary while keeping the spacecraft light enough to launch and maneuver. Early design concepts with distributed shielding throughout the spacecraft proved inadequate against Jupiter's extreme conditions. Even specialized radiation-hardened electronics would be overwhelmed without additional protection. The mission science requirements complicated matters further. Juno needed to carry sensitive magnetometers that are particularly susceptible to radiation interference. The spacecraft also required precise attitude control systems that radiation could easily disrupt. Each scientific objective added another layer of complexity to the radiation protection problem. NASA engineers eventually developed a revolutionary solution: concentrate the most sensitive electronics in a single, heavily shielded compartment. This led to the creation of Juno's titanium radiation vault, a protective fortress about the size of an SUV's trunk. Weighing approximately 400 pounds, this structure became the centerpiece of Juno's radiation mitigation strategy. The vault's walls, made of titanium 1 centimeter thick, reduce incoming radiation by a factor of 800, creating a relatively safe environment for the spacecraft's most critical components. This approach represented a significant departure from previous spacecraft designs. Rather than trying to harden each component individually, the vault strategy protected the most vulnerable systems collectively. The spacecraft's main computer, power distribution units, and most instrument control electronics were all housed within this protective shell, allowing for more effective use of shielding material while maintaining reasonable spacecraft mass. For components that couldn't be placed inside the vault, engineers employed additional strategies. They used spot shielding for exposed but sensitive parts and incorporated radiation-tolerant materials throughout the spacecraft. Mission planners also developed software routines that could detect radiation-induced errors and restart affected systems when necessary. Juno's power system required particular innovation, becoming the first solar-powered spacecraft to operate at Jupiter's distance from the Sun, where sunlight is only 4% as strong as Earth. The spacecraft's 3 massive solar panels, each extending about 29.5 feet from the main body, were the largest ever deployed on a planetary probe at that time and served the dual purpose of providing power and helping stabilize the spacecraft. As a final protective measure, mission designers created an orbital path specifically to minimize radiation exposure. Juno would approach Jupiter over the poles, avoiding the most intense regions of the radiation belts concentrated around the planet's equator. The spacecraft would follow a highly elliptical orbit, coming close to Jupiter only briefly before swinging back out to safer distances, collecting essential data during each close approach while limiting cumulative radiation exposure. The solutions developed for Juno have established new standards for spacecraft operating in extreme environments. The titanium vault concept represents a significant advance in radiation protection strategy, with applications beyond the Juno mission, potentially enabling future exploration of other high radiation environments such as Europa or even closer studies of the Sun. After years of development and testing, Juno launched in August 2011, beginning its 5-year journey to Jupiter. The true test of these engineering solutions came in July 2016 when Juno finally arrived at Jupiter and began its close-range observations. The spacecraft's survival validated NASA's innovative approaches to overcome the seemingly impossible challenge of studying Jupiter up close, allowing Juno to collect unprecedented data about the gas giant while managing the severe radiation environment that had kept previous missions at a safe distance. Juno's revolutionary orbit. Juno's approach to Jupiter required a completely new orbital strategy. No spacecraft had ever attempted such a daring flight path, taking Juno just 4,200 kilometers above Jupiter's swirling cloud tops. This distance is remarkable when you consider that Jupiter's radius is about 70,000 kilometers. At its closest approach, Juno passes closer to Jupiter than the International Space Station orbits above Earth. The mission's scientific objectives directly shape this unique orbital design. To accurately map Jupiter's gravitational field, measure its magnetic properties, and analyze its atmosphere, Juno needed to collect data from extremely close range. Previous missions maintained safer distances from Jupiter, which limited the precision of their measurements. The Galileo mission operated at much greater distances to protect its instruments from radiation damage. Juno's science team determined that only by flying directly through Jupiter's gravity and magnetic fields could they collect the detailed measurements needed to understand the planet's internal structure. This proximity created a fundamental tension between scientific needs and spacecraft safety. Flying close to Jupiter exposed Juno to intense radiation that could damage its systems, yet maintaining a safer distance would compromise the mission's scientific goals. The team developed an orbital strategy that balanced these competing demands. The solution emerged as an elongated, elliptical orbit. Mission planners designed a path that would bring Juno extremely close to Jupiter for brief periods before sending it back out to safer distances. This approach limited the spacecraft's time in the most dangerous radiation zones while still allowing it to collect critical data during each close approach. The 53-day orbital period meant Juno would spend most of its time far from Jupiter, where radiation levels are significantly lower, then dive back for short, intense observation periods. This orbit provided a revolutionary scientific perspective. By approaching Jupiter over its poles rather than around its equator, Juno became the first spacecraft to directly observe Jupiter's polar regions. Previous missions followed equatorial or low-inclination orbits that couldn't view the poles effectively. Juno's polar orbit allowed it to see areas of Jupiter that had remained hidden from human observation throughout history, essentially diving into uncharted territory with each approach. Establishing this precise orbit required meticulous calculation and timing. During its approach to Jupiter on July 4, 2016, Juno had to fire its main engine at exactly the right moment to be captured by Jupiter's gravity. This Jupiter orbit insertion maneuver was entirely autonomous due to the 48-minute communication delay with Earth. The spacecraft had to turn away from the Sun, orient itself correctly, stabilize rotation, and ignite its engine without direct human control. The burn lasted 2,102 seconds and slowed Juno by 542 meters per second, placing it into its initial capture orbit. The success of this maneuver was crucial. It established the foundation for all future scientific observations. Each 53-day orbit creates a predictable rhythm to Juno's mission. The spacecraft begins far from Jupiter, gradually accelerating as Jupiter's gravity pulls it inward. As Juno approaches, it activates its instruments and begins collecting data. The spacecraft reaches maximum velocity during its closest approach, or perihove, when it's flying just thousands of kilometers above Jupiter's clouds at speeds exceeding 200,000 kilometers per hour. After this intensely productive period, Juno swings back out to its maximum distance of about 8 million kilometers. Originally, mission planners intended to reduce this orbit to a shorter 14-day orbit after initial observations. However, concerns about the main engine's valves led to maintaining the 53-day orbit throughout the primary mission. This choice extended the timeline, but created unexpected scientific opportunities, allowing Juno to explore regions dominated by Jupiter's magnetic field more extensively. Maintaining this orbit presents significant challenges. Jupiter's massive size creates a complex gravitational field that can gradually alter Juno's trajectory. The spacecraft must perform periodic adjustments using its thrusters to maintain the desired flight path. Additionally, the extreme radiation environment can affect the spacecraft's systems, requiring constant monitoring from mission controllers. Each close approach represents both risk and extraordinary scientific opportunity. During these periods, Juno flies through radiation levels that would quickly damage unprotected electronics. Despite its titanium radiation vault, Juno has experienced several safe mode events during close passes. These events trigger automatic shutdown of non-essential systems to protect the spacecraft. However, each perihove also provides unprecedented data collection opportunities, with instruments measuring magnetic fields, gravitational variations, and atmospheric composition with remarkable precision. The scientific payoff from this orbital strategy has been remarkable. Juno's close-range observations have shown that Jupiter's weather systems extend to depths of about 3,000 kilometers. The mission discovered that Jupiter's magnetic field is significantly more complex than earlier models suggested, with unusual concentrations in the northern hemisphere. Most significantly, Juno's orbit provided humanity's first direct observations of Jupiter's poles. When Juno's cameras finally captured these regions, they revealed structures unlike anything seen elsewhere in the solar system. Instead of patterns similar to Saturn's hexagon, Juno discovered clusters of massive cyclones arranged in geometric formations. In the north, 8 cyclones surround a central storm, while the South Pole hosts 5 similarly arranged cyclones. The success of Juno's orbital strategy has led to the mission's extension through 2025, allowing additional orbits and expanded observations of Jupiter's ring system and moons. Each orbit continues to provide new data, gradually building a more complete picture of Jupiter's complex systems. The surprise at Jupiter's poles. Before Juno, scientists had never directly observed Jupiter's poles. Earth-based telescopes could only view the planet's equatorial regions effectively, while previous spacecraft missions followed orbital paths that kept them near Jupiter's equator. This left Jupiter's poles as mysterious territories, visible only at oblique angles that revealed little detail about their structure or dynamics. Scientists made reasonable assumptions about what they might find based on observations of Saturn, the other large gas giant in our solar system. Saturn's North Pole features a striking hexagonal cloud pattern, discovered by the Voyager mission and later studied in detail by the Cassini spacecraft. This hexagon, a wave-like jet stream that flows around the pole at about 200 miles per hour, has maintained its six-sided shape for decades. Given the similarities between Saturn and Jupiter, many scientists anticipated Jupiter might display comparable geometric features at its poles. As Juno approached Jupiter in 2016 and prepared for its first polar pass, the scientific team eagerly anticipated their first clear view of these unexplored regions. Would Jupiter's poles mirror Saturn's organized structure, or would they simply show extensions of the familiar banded patterns seen at lower latitudes? The team prepared their hypotheses, ready to interpret what they expected would be variations on familiar planetary atmospheric patterns. When Juno's first images of Jupiter's poles arrived back on Earth, the scientific team was stunned. "We were wrong about everything," admitted one Juno mission scientist during an early press conference. Juno revealed something entirely unexpected. Clusters of massive cyclonic storms arranged in surprisingly organized formations around each pole. At the North Pole, Juno observed a central cyclone surrounded by 8 additional cyclones, all arranged in a remarkably regular octagonal pattern. Each of these storms measures approximately 2,500 miles across, roughly the distance from New York to Los Angeles. A single Jovian cyclone could cover most of the continental United States. Their spiral arms visibly touch neighboring storms, yet they maintain their individual identities and positions. Jupiter's South Pole showed a similar but distinct arrangement, 5 cyclones surrounding a central storm in a pentagonal pattern. Later observations revealed a 6th cyclone had somehow muscled in on this arrangement, creating an even more complex configuration. The sizes of these southern storms are equally massive, with diameters comparable to their northern counterparts. These cyclones represent atmospheric structures unlike anything seen elsewhere in our solar system. Wind speeds in these massive storms have been measured at over 220 miles per hour, stronger than the most intense Category 5 hurricanes on Earth. Perhaps more surprising than their existence is the stability of these cyclonic formations. On Earth, when hurricanes approach each other, they typically interact in a process called the Fujiwara affect, where they orbit each other and eventually merge or disperse. The Jovian polar cyclones, despite their spiral arms touching, have maintained their positions and individual structures for years. This stability presents a significant scientific mystery. According to conventional fluid dynamics, these tightly packed vortices should interact, merge, or repel each other. Yet they remain locked in their geometric arrangements over extended periods. Scientists have begun developing new models to explain how these massive cyclones maintain their positions without combining into a single giant storm. One emerging theory suggests that the cyclones are kept separate by smaller anticyclonic storms positioned between them. These smaller storms may act as barriers, preventing the larger cyclones from merging. Another hypothesis proposes that deeper atmospheric layers beneath the visible clouds provide stabilizing forces that maintain the cyclone's positions. Juno's thermal infrared imaging added another layer to the mystery. Temperature mapping revealed the cores of these cyclones registering as surprisingly warm compared to surrounding areas. This temperature difference suggests these storms extend deep into Jupiter's atmosphere, potentially connecting to heat sources far below visible cloud layers. The infrared data also showed sharp temperature boundaries between the cyclones and surrounding regions, indicating these storms effectively trap heat within their circulation patterns. These temperature gradients may contribute to the storm's stability, creating energy barriers that prevent them from merging with neighboring cyclones. Color differences visible in Juno's images provide additional clues about the composition of these polar storms. The cyclones appear bluish compared to Jupiter's typical tan and orange cloud bands, suggesting different chemical compositions or cloud heights in these regions. The blue coloration likely indicates clouds at higher altitudes where temperatures are colder. What makes Jupiter's poles truly unique in our solar system is this combination of features. Massive cyclones arranged in geometric patterns that remain stable over years despite their proximity to each other. The poles represent a completely different atmospheric regime than Jupiter's famous banded structure at lower latitudes with different organizing principles and dynamics. The discovery of these polar structures has forced scientists to rethink fundamental assumptions about gas giant atmospheres. The traditional view of Jupiter's atmosphere as a system of east-west flowing bands dominated by the Great Red Spot has now expanded to include these complex polar regions with their own distinct patterns and behaviors. These unexpected findings have prompted researchers to develop new atmospheric models that might explain not only Jupiter's cyclones, but potentially improve our understanding of complex weather systems on Earth and other planets. The mechanisms maintaining Jupiter's polar cyclones might provide insights into how large-scale atmospheric features form and persist in various planetary environments. As Juno continues its extended mission, scientists are tracking how these polar structures evolve over time. Small changes have been observed in the positions of individual cyclones, but the overall geometric patterns have remained remarkably consistent. These discoveries remind us that even familiar objects in our solar system seeing through Jupiter's clouds. When we look at Jupiter through a telescope, we see a beautiful world of swirling clouds, colorful bands, and the iconic Great Red Spot. These features have captivated astronomers since Galileo first observed the planet in 1610. However, this familiar view of Jupiter represents only the thinnest outer shell of an incredibly deep and complex atmosphere. The cloud tops that create Jupiter's distinctive appearance sit like a thin skin atop a massive atmospheric system that extends hundreds of kilometers into the planet. Our understanding of Jupiter was limited to this uppermost layer, effectively just the ceiling of Jupiter's atmosphere. Much like an iceberg with only its tip visible above water, the vast majority of Jupiter's atmospheric structure remained hidden from view. Scientists could observe the movement of clouds, track storms, and measure temperatures, but the forces driving these phenomena remained concealed beneath the visible surface. The atmospheric features we observe on Jupiter exist within a shallow layer approximately 50 kilometers deep. Yet Jupiter's atmosphere extends thousands of kilometers below this visible region. The clouds we see consist primarily of ammonia crystals at the highest altitudes, with ammonium hydrosulfide and water-based clouds forming at progressively deeper levels. These different cloud layers create Jupiter's multicolored bands, but they also block our view of anything deeper, effectively hiding most of Jupiter's atmosphere from conventional observation methods. Critical questions about Jupiter remained unanswered. How deep do the atmospheric circulation patterns extend? How does energy move through different layers of the atmosphere? What is the water content in Jupiter's deep atmosphere, a crucial factor for understanding the planet's formation? Uncovering these hidden planetary landscapes required technology that could penetrate beyond the colorful ceiling of clouds. The solution came in the form of the microwave radiometer, MWR, a sophisticated instrument specifically designed for the Juno mission to probe Jupiter's deep atmosphere. This revolutionary tool would allow scientists to peer into the mysterious depths, revealing the invisible structures beneath Jupiter's visible face. The MWR works on a fundamentally different principle than cameras. Rather than capturing reflected sunlight, it detects thermal emissions, the natural microwave radiation generated by the heat within Jupiter itself. This radiation can pass through clouds that block visible light, allowing the instrument to detect signals from far below the visible surface. The technology functions similarly to weather radar on Earth, but with far greater sophistication and sensitivity. Juno's microwave radiometer consists of 6 antennas mounted on the sides of the spacecraft, each tuned to a specific microwave frequency, 600 MHz, 1.2, 2.4, 4.8, 9.6, and 22 gigahertz. These frequencies represent specific windows in the electromagnetic spectrum where Jupiter's atmosphere is partially transparent, allowing microwave radiation to pass through from different depths. Each frequency corresponds to a different atmospheric depth. The longest wavelength, 600 megahertz, can detect radiation from as deep as 500 to 600 kilometers below the cloud tops, while the shortest wavelength, 22 gigahertz, provides information about the uppermost atmosphere. By analyzing the signals across all 6 frequencies, scientists can construct a vertical profile of Jupiter's atmosphere, mapping temperature, composition, and structure at different levels simultaneously. For the first time, scientists could create 3-dimensional maps of Jupiter's atmosphere, seeing how structures and composition change with depth. The MWR allows scientists to peel back Jupiter's cloud layers one by one, revealing the complex dynamics occurring beneath the visible surface. Implementing this technology presented numerous technical challenges. The MWR had to operate with extreme precision while the spacecraft traveled at over 200,000 kilometers per hour during its closest approaches to Jupiter. The antennas needed to maintain a clear field of view despite the spacecraft's rotation. Additionally, the instrument had to function in Jupiter's intense radiation environment, which could potentially interfere with its sensitive receivers. The microwave signals don't translate directly into simple images like those from a camera. They provide complex patterns of radiation intensity that must be analyzed through sophisticated computer models. Scientists developed new techniques to convert these microwave measurements into meaningful information about Jupiter's hidden structure. When the first MWR data arrived from Juno, it revealed an atmosphere far more complex and dynamic than anyone had anticipated. The familiar weather patterns, the colorful bands and spots visible from Earth, extend much deeper into the planet than previously thought. The atmospheric jet streams that create Jupiter's distinctive bands reach depths of about 3,000 kilometers below the cloud tops, far deeper than equivalent features on Earth or other planets. This discovery was surprising because scientists had generally assumed that Jupiter's weather would be confined to a relatively shallow layer near the surface. Instead, Jupiter's atmospheric circulation involves a much more substantial portion of the planet's total mass. This finding suggests that Jupiter's weather systems are driven by forces fundamentally different from those on Earth, possibly connected to the planet's internal heat sources and rapid rotation. The MWR also provided crucial new data about water distribution in Jupiter's atmosphere, a key factor in understanding how the planet formed. Perhaps most surprisingly, the data revealed massive cyclonic structures extending hundreds of kilometers into Jupiter's atmosphere. These deep atmospheric structures connect to the surface features we observe, creating complex 3-dimensional weather systems unlike anything seen on Earth. These discoveries have profound implications for our understanding of Jupiter's formation and evolution. The distribution of water and other materials provides clues about how Jupiter formed in the early solar system. The deep atmospheric dynamics suggest mechanisms by which Jupiter has evolved over billions of years, potentially changing our models of how gas giants develop over cosmic timescales. As scientists continue to analyze data from the MWR, they uncover more surprises about Jupiter's internal structure, including unusual energy transfer mechanisms that contradict standard physical models and suggest processes unique to Jupiter's massive, rapidly rotating atmosphere. Jupiter's atmospheric energy puzzle. When studying fluid systems like Earth's atmosphere or ocean currents, physicists rely on well-established principles that describe how energy moves and dissipates. According to these standard models, energy in turbulent systems follows a predictable path. It transfers from larger structures to progressively smaller ones, eventually converting into heat at the smallest scales. This process, known as the energy cascade, forms the foundation of our understanding of fluid dynamics across the universe. Scientists naturally expected Jupiter's atmosphere to follow these same fundamental principles. The energy cascade model has proven remarkably reliable in natural systems. From Earth's weather patterns to laboratory experiments, we consistently observe large structures breaking down into smaller ones before eventually dissipating as heat. This pattern appears so consistently that scientists considered it a universal property of turbulent fluids. Jupiter, despite its massive scale, should theoretically obey these same physical laws. Jupiter's immense size and rapid rotation create an atmosphere dominated by powerful jet streams that form the planet's distinctive colored bands. Scientists expected these large-scale structures to gradually shed their energy to smaller vortices and ultimately dissipate through friction and turbulence. Computer models of Jupiter's atmosphere, built on these standard fluid dynamics principles, predicted certain patterns of energy flow that aligned with our terrestrial experience. When Juno began measuring Jupiter's atmospheric dynamics with unprecedented precision, the data revealed a profound surprise. The spacecraft's instruments detected energy flowing in the opposite direction from what physics predicts, a cosmic reversal of nature's expected rhythm. Instead of large structures breaking down into smaller ones, Jupiter's atmosphere showed energy moving from smaller features toward larger structures, contradicting the standard models that had successfully described fluid behavior in countless other contexts. Juno's measurements identified what scientists call an inverse energy cascade, where turbulent energy moves upscale rather than downscale. Small-scale atmospheric vortices tens of kilometers across transfer their energy to progressively larger structures. This process ultimately powers and maintains Jupiter's massive weather systems, including the enormous jet streams that span the entire planet in storms like the Great Red Spot that dwarf Earth itself. This reversed energy flow represents a fundamental challenge to our understanding of fluid systems. The phenomenon appears similar to an ecosystem where energy somehow accumulates at the top of the food chain rather than being distributed downward, a complete inversion of expected natural order. The mathematical models incorporating standard Navier-Stokes equations failed to predict this behavior, suggesting either that additional factors need consideration or that the basic equations themselves might require modification when applied at planetary scales. The inverse cascade explains one of Jupiter's most puzzling features, its atmospheric stability. Jupiter's banded structure has remained remarkably consistent for centuries, with only minor variations in band positions and widths. The Great Red Spot has persisted for at least 400 years, defying expectations that such a massive storm should dissipate relatively quickly. The inverse energy cascade provides a continuous supply of energy to these large-scale features, allowing them to persist despite the forces that should tear them apart. Scientists have begun developing new mathematical frameworks to explain this behavior. Some models incorporate the effects of Jupiter's rapid rotation and deep atmospheric structure, suggesting that these factors might create conditions where inverse energy cascades become dominant. Others explore how the planet's internal heat flow interacts with its atmosphere, potentially creating energy sources that behave differently from the solar heating that drives Earth's weather. This discovery challenges the assumption that standard energy cascade mechanics apply universally to all fluid systems. If different energy transfer mechanisms dominate at planetary scales, scientists may need to reconsider how they model other gas giants in our solar system and exoplanets orbiting distant stars. The finding potentially opens an entirely new branch of fluid dynamics research focused on these alternative energy pathways. The implications extend to our understanding of planetary evolution. If energy consistently flows toward larger structures in Jupiter's atmosphere, this process may have played a crucial role in shaping the planet's appearance over billions of years. The stable band structure and persistent storms might represent the natural end state of a system, where energy accumulates in large-scale features rather than dissipating. For researchers studying Earth's climate and weather systems, Jupiter's unusual energy transfer raises intriguing questions. While Earth's atmosphere generally follows the standard cascade model, certain large-scale atmospheric phenomena might incorporate elements of inverse energy flow under specific conditions. Understanding Jupiter's atmosphere could provide insights into unusual weather patterns on Earth and potentially improve our climate models. This discovery highlights how much remains unknown about even the basic physics governing planetary systems. Jupiter orbits relatively close to Earth and has been studied for centuries, yet its atmosphere operates according to principles that weren't anticipated by our best physical models. This revelation reminds us that fundamental discoveries await even in seemingly familiar territory. The energy puzzle in Jupiter's atmosphere illustrates why direct measurement remains essential for scientific progress. Without Juno's close-up measurements, this surprising energy behavior might have remained undiscovered indefinitely, hidden behind the limited view of Jupiter's cloud tops. As scientists continue analyzing Juno's data, they hope to develop a more complete understanding of these nonlinear energy transfer mechanisms. Jupiter's atmospheric energy puzzle stands as one of the most significant discoveries from the Juno mission, challenging fundamental assumptions about fluid behavior on planetary scales. But this was just one of several major surprises that would emerge from Juno's observations. As the spacecraft continued its orbital dance with Jupiter, it revealed another completely unexpected feature of the gas giant, a magnetic field with a structure that scientists had thought physically impossible. The magnetic field that shouldn't exist. Every planet with a magnetic field in our solar system follows a similar pattern. The field typically resembles what you'd see with a simple bar magnet, flowing smoothly from one pole to the other with lines of magnetic force that form a predictable symmetrical shape. Earth's magnetic field follows this pattern, as do the fields of Mercury, Saturn, Uranus, and Neptune. When planning the Juno mission, scientists naturally expected Jupiter to conform to this same basic structure, just with a much stronger field. Planetary magnetic fields originate through a process called the dynamo effect. Deep within a planet, electrically conducting fluid materials, typically molten iron in rocky planets or metallic hydrogen in gaseous giants, flow and rotate. This movement of conductive material, combined with the planet's rotation, generates electric currents that produce a magnetic field. The mathematics governing this process suggest that a planetary magnetic field should emerge with a relatively organized, dipolar structure, essentially a north and south magnetic pole aligned roughly with the planet's rotational axis. Jupiter's magnetic field was already known to be extraordinary in its strength, about 20,000 times more powerful than Earth's. Previous spacecraft had measured this field from a distance, confirming its immense magnitude, but lacking the precision to map its detailed structure. Scientists expected Juno would find a more powerful version of the standard planetary magnetic field pattern, perhaps with minor localized variations. When Juno completed its first few orbits and began mapping Jupiter's magnetic field in detail, the data revealed something entirely unexpected. Rather than the symmetric field structure scientists anticipated, Jupiter's magnetic field showed a dramatic asymmetry between its northern and southern hemispheres. This asymmetry represented a fundamental difference in how the magnetic field behaves in each hemisphere, defying standard models of planetary magnetism. In the northern hemisphere, Jupiter's magnetic field exhibits an extremely unusual pattern that scientists described as sprouting like weeds. Instead of the smooth, organized field lines typical of planetary magnetic fields, the northern hemisphere shows multiple spots where the magnetic field emerges from or plunges into the planet. These magnetic flux concentrations create a chaotic, tangled pattern unlike anything observed elsewhere in the solar system. The field intensity varies dramatically across relatively short distances with complex structures that appear almost random. The southern hemisphere, by contrast, presents a completely different magnetic signature. While not perfectly matching the standard dipole model, the southern magnetic field is much more organized and concentrated. It features fewer but stronger magnetic flux regions and generally behaves more like what scientists expected based on existing theories. The stark contrast between the two hemispheres created a profound scientific mystery. How could a single planet generate two fundamentally different magnetic field structures on either side of its equator? This north-south asymmetry violates basic assumptions about how planetary dynamos function. The standard theory suggests that the processes generating a magnetic field should operate similarly throughout a planet's interior, producing a field with broad symmetry between hemispheres. The dramatic contrast observed at Jupiter suggests something fundamentally different is happening inside the gas giant. The discovery of what scientists named the Great Blue Spot further complicated the picture. This feature, not actually blue but named for the color used on magnetic field maps, represents an intense concentration of magnetic flux near Jupiter's equator. It behaves almost like a second south magnetic pole emerging from an unexpected location. This single feature fundamentally changes our understanding of giant planet magnetism, notes planetary scientist Kimberly Moore of Harvard University. We've never seen anything like this before. The Great Blue Spot drifts westward due to Jupiter's atmospheric jet streams, with its motion changing every 4 years. This dynamic behavior suggests complex interactions between Jupiter's interior and its atmospheric circulation. This asymmetric magnetic field structure presents significant challenges to our scientific understanding of planetary interiors. The models that successfully explain magnetic field generation on Earth and other planets fail to account for Jupiter's unusual magnetic configuration. According to standard dynamo theory, such a dramatic hemispheric asymmetry shouldn't be stable over long periods, yet Jupiter's field appears to maintain this asymmetric structure. The implications for our understanding of gas giant interiors are profound. Jupiter's interior structure must be significantly different from previous models to generate such an unusual magnetic field. The traditional model of Jupiter's interior includes a relatively small, rocky, metallic core surrounded by a layer of metallic hydrogen, topped by an outer layer of molecular hydrogen. But Juno's magnetic measurements suggest this simple layered model is inadequate. The hemispheric differences in the magnetic field likely indicate corresponding differences in the flow patterns or composition of Jupiter's interior. Perhaps the metallic hydrogen layer has different properties in the northern versus southern hemispheres. Alternatively, Jupiter's core might be offset from the planet's center or have an asymmetric composition that influences the dynamo process differently in each hemisphere. Jupiter's mysterious magnetic asymmetry may also provide clues about the planet's formation and evolution. The unusual field structure might reflect asymmetries in how material accreted during Jupiter's formation or could indicate major impacts early in the planet's history. This discovery forces scientists to reconsider fundamental aspects of dynamo theory. The mathematical models that successfully describe magnetic field generation on Earth require modification to account for Jupiter's bizarre field structure. As planetary scientist Scott Bolton explains, Jupiter's magnetic field is completely unlike anything we've seen before. As Juno continues its extended mission until 2025, additional measurements will allow scientists to track how the field changes over time and potentially identify patterns that might explain its unusual structure. Each new orbital pass provides more data points, gradually building a more complete picture of Jupiter's extraordinary magnetic environment. Rethinking Jupiter's interior. For decades, our understanding of Jupiter's interior followed a clean, elegant model. Scientists envisioned the gas giant as having a layered structure with distinct boundaries, much like an onion. At the center sat a compact core of heavy elements like iron and silicon, roughly 10 times Earth's mass. Surrounding this core, we believe there was a layer of metallic hydrogen, where immense pressure forces hydrogen to behave like a liquid metal, conducting electricity and generating Jupiter's magnetic field. Above this, the model proposed a thick layer of molecular hydrogen, topped finely by the visible cloud layers we can observe from Earth. This straightforward structure made theoretical sense and aligned with our understanding of how gas giants form and evolve. This traditional model served as the foundation for planetary formation theories. It suggested Jupiter formed through a bottom-up process called core accretion, where a solid core formed first, growing large enough to rapidly attract surrounding hydrogen and helium gas. This neatly layered structure explained Jupiter's composition, energy output, and observable properties while providing a template for understanding gas giant formation throughout the universe. What we thought we knew about Jupiter, however, would soon be challenged. When Juno began precisely measuring Jupiter's gravitational field, the data revealed something completely unexpected. The spacecraft detected subtle variations in Jupiter's gravity that contradicted the clean, layered model. Juno accomplishes these measurements through an ingenious technique. Scientists track tiny shifts in the spacecraft's radio signal as Jupiter's gravity field pulls on it during each close approach. These minuscule frequency shifts, sometimes just a fraction of a hertz, reveal the internal mass distribution of the planet with extraordinary precision. Imagine expecting to find a perfectly layered cake, only to discover the ingredients had mysteriously blended together. The gravity data painted a picture of Jupiter's interior that was far more complex and mixed than anyone had anticipated. Instead of clear boundaries between layers, Juno's measurements suggested a gradual blending between regions. The core appeared to be larger, but less dense than expected, with heavy elements partially dissolved and distributed throughout the surrounding hydrogen rather than neatly concentrated at the center. The traditional boundaries between metallic and molecular hydrogen regions appeared blurred, suggesting a more gradual transition between these states. These findings indicate that Jupiter's interior is remarkably non-uniform, with complex flows and mixing processes occurring throughout the planet. Rather than maintaining stable, separate layers over billions of years, Jupiter's interior appears dynamic and interactive, with materials moving between regions in ways not predicted by simpler models. Scientists now believe that the heavy elements that should form Jupiter's core are partially dissolved into the surrounding hydrogen, creating a fuzzy core that extends to nearly half of Jupiter's radius. This discovery has significant implications for understanding Jupiter's formation and evolution. The mixed interior suggests that Jupiter may not have formed through the simple core accretion process previously imagined. Instead, the planet might have experienced a more complex formation history, possibly including giant impacts with other large protoplanets during the early solar system. Such collisions could have disrupted any original layered structure, mixing materials that would otherwise remain separated. Another possibility is that Jupiter's interior has evolved substantially since its formation. Over billions of years, processes like convection and diffusion might have gradually eroded the boundaries between layers, creating the mixed structure we observe today. This suggests Jupiter is not a static, unchanging world, but a dynamic planet that continues to evolve internally even after billions of years. Based on Juno's data, scientists have developed revised models of Jupiter's core structure. Rather than a small, compact core, these new models propose an extended dilute core region where heavy elements are concentrated, but partially mixed with hydrogen. This region might extend to as much as 0.3 to 0.5 of Jupiter's radius, much larger than the previous estimate of 0.1. These new insights about Jupiter's internal structure have profound implications for our understanding of gas giant formation throughout the universe. If Jupiter, the closest and most studied gas giant, doesn't match our theoretical models, then our understanding of exoplanetary systems likely requires significant revision as well. The thousands of exoplanets discovered around other stars include many gas giants that astronomers have analyzed based on models derived from our understanding of Jupiter. The complex mixed interior structure also helps explain the unusual magnetic field configuration observed by Juno. The traditional dynamo models assumed a relatively uniform, metallic hydrogen layer generating Jupiter's magnetic field. A more complex, non-uniform interior with gradual transitions and mixed materials would naturally produce a more complex magnetic field structure. Understanding Jupiter's formation history provides crucial context for the development of our entire solar system. As the largest planet, Jupiter's formation dramatically influenced the evolution of other planets, including Earth. Its massive gravitational pull shaped the orbits of smaller bodies, directed material toward or away from the inner solar system, and likely played a key role in delivering water and other essential compounds to the terrestrial planets. Jupiter's revised internal structure also connects to ongoing questions about the planet's atmospheric behavior. The unexplained energy transfer mechanisms observed in Jupiter's atmosphere may originate from this complex internal structure, with the blurred boundaries between regions creating unique conditions for heat and energy flow throughout the planet. As Juno continues its extended mission, it reveals new details about Jupiter itself while also gathering unprecedented data about the planet's moons. These observations are expanding our understanding of the entire Jovian system. The spacecraft has observed massive volcanic plumes erupting from Io's surface and mapped temperature changes associated with its extreme volcanic activity. The revolutionary findings about Jupiter's interior remind us why direct measurement remains essential for scientific progress. Even with our most sophisticated models and theories, nature continues to surprise us when we look more closely. Jupiter, a planet we've studied for centuries, still conceals fundamental secrets about its formation and evolution. New discoveries about Jupiter's volcanic moon, Io. Jupiter's immense gravitational pull doesn't just shape its own complex systems, it transforms the worlds around it. While Juno's primary mission focused on Jupiter itself, the spacecraft has unexpectedly delivered groundbreaking discoveries about Io, the innermost of Jupiter's 4 Galilean moons. This small world, roughly the size of our own moon, holds the distinction of being the most volcanically active body in our entire solar system. Io presents a dramatic vision of primordial power, a world constantly reborn in fire. Its mottled surface displays yellows, reds, and browns, creating what scientists describe as a pizza-faced appearance. These colorful patches are vast deposits of sulfur and volcanic materials from hundreds of active volcanoes that completely resurface Io every few million years, an incredibly rapid pace by geological standards. The source of this extraordinary activity lies in Io's orbital position. The moon completes an orbit around Jupiter every 42.5 hours in an elliptical path. Combined with the gravitational pull of Jupiter's other large moons, this creates intense tidal forces. As Io orbits, Jupiter's gravity stretches and compresses the moon, generating tremendous internal friction. This friction produces enormous heat that powers Io's extreme volcanic activity. Juno wasn't specifically designed to study Io in detail. The spacecraft's instruments were optimized for Jupiter's clouds and fields. Yet the mission team adapted these tools to observe Io during close flybys, yielding insights that surprised even veteran researchers. During a December 27, 2024 flyby, Juno detected something extraordinary. A massive volcanic hotspot in Io's southern hemisphere larger than Earth's Lake Superior. This volcanic event represents the most powerful ever recorded on Io, spanning approximately 40,000 square miles, 100,000 square kilometers of the surface. The energy output from this eruption is staggering, approximately 6 times more than all Earth's power plants combined. This massive outpouring continues to reshape Io's southern hemisphere. When Juno passed by again on March 2, 2025, the eruption was still actively spewing lava and ash, demonstrating the sustained nature of Io's volcanic processes. JunoCam, the spacecraft's visible light camera, captured images showing significant surface changes near Io's south pole associated with this eruption. Comparing images from previous flybys with recent observations, scientists noted dramatic color changes in the region, providing visual confirmation of the ongoing volcanic activity detected by infrared instruments. Juno's Jovian Infrared Auroral Mapper, GRIM, has been crucial in mapping these thermal features on Io's surface. The instrument, designed to study Jupiter's atmospheric heat patterns, proved remarkably effective at identifying volcanic hotspots on Io. GRIM's data revealed not just the location, but the temperature and scale of volcanic features across Io's constantly changing surface. The microwave radiometer, MWR, originally designed to study Jupiter's deep atmosphere, has been creatively repurposed to observe Io's subsurface. This revealed unprecedented insights into the moon's temperature profile, showing evidence of cooling lava flows beneath Io's surface, vast regions where magma remains warm but hasn't fully solidified. These subsurface measurements suggest approximately 10% of Io's entire surface is covered with slowly cooling lava remnants. The cooling flows function similar to a car radiator, efficiently transferring heat from the interior to the surface where it radiates into space. This efficient mechanism helps explain how Io maintains its extraordinary volcanic activity. The combination of multiple instrument data has created a more comprehensive picture of Io's interior. Previous theories from NASA's Galileo mission suggested Io might contain a global subsurface magma ocean. However, Juno's detailed gravity measurements suggest a different scenario. rather than a global magma ocean. Juno's data supports the idea that Io operates in a height pipe regime. In this model, volcanic melt can be delivered to the surface through discrete channels so efficiently that it prevents forming a continuous magma ocean. Instead, Io likely contains localized magma reservoirs feeding specific volcanic systems, a major shift in understanding how Io's interior operates. The mission team plans to collect additional observations during upcoming flybys, including one scheduled for May, when Juno will pass within approximately 55,300 miles, 89,000 kilometers, of Io. These continuing observations will monitor the massive southern eruption's evolution and potentially detect new volcanic features. These discoveries connect to broader questions in planetary science. Io represents an extreme case of tidal heating, a process affecting many worlds throughout our solar system. Understanding how Jupiter's tidal forces drive Io's volcanism provides insights applicable to other moons, including Europa and Enceladus, where similar but less intense tidal heating maintains subsurface oceans. Jupiter's influence on Io provides a natural laboratory for studying processes that shaped early Earth and other terrestrial planets. The volcanic processes reshaping Io today resemble those on Earth billions of years ago when our planet was more geologically active. Studying these processes on Io provides insights into Earth's early history. The discoveries about Io's localized magma reservoirs challenge assumptions about similar processes on other celestial bodies. The findings may serve as a template for exploring internal dynamics of other worlds within our solar system and beyond. Juno's observations demonstrate how a mission designed for one purpose can yield unexpected dividends in different areas. By using instruments creatively, scientists gain valuable insights about one of the most geologically fascinating worlds in our solar system. As Juno continues its extended mission until 2025, each observation adds another piece to our understanding of this dynamic world and its relationship with Jupiter. Rewriting the textbooks on gas giants. When NASA's Juno spacecraft arrived at Jupiter in 2016, scientists had reasonable confidence in their understanding of gas giants. After all, astronomers had studied Jupiter for centuries, and previous missions like Pioneer, Voyager, and Galileo had provided valuable data about the planet's composition, cloud patterns, and magnetic properties. Jupiter represented our template for understanding gas giants throughout the universe. It was supposed to be the gas giant we understood best. 5 years and dozens of orbits later, Juno has transformed our understanding of Jupiter in ways no one expected. Nearly every major assumption about gas giants has been challenged by Juno's findings. From Jupiter's atmospheric dynamics to its magnetic field structure and interior composition, the spacecraft has revealed a planet far more complex and mysterious than our previous models suggested. These discoveries represent fundamental shifts in how scientists understand gas giant planets. The scope of contradicted assumptions is remarkable. Jupiter's atmosphere transfers energy in the opposite direction from fluid dynamics predictions. Its magnetic field displays a north-south asymmetry that contradicts standard dynamo theory. Its interior lacks the clear boundaries between layers that featured in textbooks for decades. Its poles host stable geometric arrangements of cyclones that defy explanation. Each discovery alone requires significant revisions to existing models. Together, they necessitate a comprehensive rethinking of gas giant physics. These findings have profound implications for our models of planetary formation and evolution. The traditional core accretion model suggests gas giants form an overly straightforward process. A solid core of rock and ice accumulates until it's massive enough to rapidly attract surrounding hydrogen and helium gas. This model predicted Jupiter should have a compact core of heavy elements surrounded by distinct layers. Juno's gravity measurements tell a different story, revealing a fuzzy core spread across nearly half of Jupiter's diameter. This unexpected core structure has led scientists to propose a new hypothesis. Something massive struck Jupiter early in its life, mixing material from the core with the hydrogen and helium that makes up most of the planet. This impact theory represents a significant departure from the smooth, gradual formation process previously assumed. If correct, it suggests that catastrophic events may play a more important role in gas giant formation than previously recognized. As Dr. Scott Bolton, Juno's principal investigator, explains, with Jupiter as the archetype of a giant planet here in our solar system, research findings there have powerfully enhanced our understanding of giant planets across the galaxy. This enhanced understanding acknowledges a level of complexity previous models failed to capture. Gas giants appear to be more dynamic, internally active, and structurally varied than scientists had anticipated. The implications extend beyond individual planets to our understanding of entire planetary systems. Current models often assume gas giants develop in a relatively predictable fashion. If Jupiter's formation involved major impacts and complex internal processes, similar events likely occurred elsewhere. This forces scientists to reconsider the conditions that lead to stable planetary configurations and the likelihood of finding Earth-like planets in habitable zones. For exoplanet researchers, Juno's findings create both challenges and opportunities. The thousands of exoplanets discovered include many gas giants whose properties have been estimated based on models derived from Jupiter. If these models require significant revision, our interpretations of exoplanet observations may need adjustment as well. The unexpected properties observed at Jupiter might be common throughout the universe, suggesting exoplanets may be even more diverse and complex than currently assumed. Jupiter's weather systems exhibit surprising properties. The mission revealed Jupiter's mid-latitudes may feature hail-like storms of ammonia-soaked mush balls. These unusual precipitation forms, combined with the planet's unusual energy patterns and stable polar cyclone arrangements, suggest atmospheric processes fundamentally different from Earth's. These findings require new mathematical models that account for behaviors not predicted by traditional fluid dynamics. Observations of Jupiter's moons have yielded additional insights. By repurposing instruments designed to study Jupiter itself, the mission team has gathered unprecedented data about Io's volcanic activity. The discovery that about 10% of Io's surface contains remnants of cooling lava helps explain how the moon renews its surface and expands our understanding of how thermal energy moves through planetary bodies. Even as Juno answers long-standing questions about Jupiter, it raises new ones that will occupy scientists for decades. How does Jupiter maintain its bizarre magnetic field structure? What processes drive its unusual atmospheric energy transfer? How did its complex interior structure evolve over 4.5 billion years? How common are these unexpected properties among gas giants throughout the universe? Scientists are now developing completely new models of gas giant formation and evolution that incorporate the complexity and dynamism revealed by Juno. These revised theories move beyond the simplified layered structures of previous models. They represent a fundamental shift in how scientists understand these massive worlds. These theoretical advances establish new foundations for interpreting observations of other planets both within and beyond our solar system. They inform the design of upcoming missions like Europa Clipper and JUICE, Jupiter Icy Moons Explorer, and provide essential context for interpreting the thousands of exoplanets discovered by telescopes. As Juno continues its extended mission until 2025, each close approach provides new data that further refines these emerging models. The mission's legacy will be a completely transformed understanding of gas giants, not as simple layered spheres, but as complex, dynamic worlds with unexpected properties and behaviors. This knowledge will guide the next generation of planetary scientists as they explore the mysteries of our solar system and countless planetary systems throughout our galaxy. Juno continues orbiting Jupiter until September 2025, gathering data that reveals new facets of this complex world with each pass. The spacecraft's extended mission includes close observations of Jupiter's rings and moons, particularly Ganymede, Europa, and Io. These investigations will help scientists refine models of planetary formation and atmospheric dynamics. The discoveries from Juno create a foundation for future exploration, directly informing ESA's JUICE mission and NASA's Europa Clipper launching this decade. By comparing Jupiter's atmospheric patterns with Earth's, researchers gain insights applicable to our own weather systems. What lies beneath those swirling clouds? Jupiter remains a cosmic